Hi everyone, in this lecture we're going to be talking about atoms, so we're really getting into the chemistry now, or getting out of the mathy little prerequisite stuff and more into the actual chemistry itself. So we're going to first define what an atom is. We're also going to describe what makes up an atom, and then we're going to kind of work backwards from how your textbook explains it, and then explain, well, where do these particles come from? How did we come to reckon that these particles exist, right? And there's a couple experiments that we'll discuss. Okay, so maybe one day, just sitting around, in a shower thought, so to speak, when you're in the shower, you get weird thoughts in your head. Sorry, that sounded really bad, but maybe you've thought to yourself as a child, what is life comprised of? If I split, and in fact, I'll give you my personal understanding of atoms. I think every human has had this. If you have sat down in your car, for example, maybe if you're like me, you thought, well, what if you have a cow, okay? So I'll do my best to draw a cow here. So maybe something like this, right? Okay, well, what if you split the cow in half, okay? These are the thoughts that a young child would have, and you'd say, well, you have half a cow, right? And what happens if you split it in half again? Well, then you have a fourth a cow. Or in my case, I said a steak, okay, which is weird. But let's say you keep cutting the cow up, right, until you're left with basically nothing. What do you get? What if I split it up so many freaking times that it's just so indefinitely small? Well, that is in essence what an atom is. An atom is the smallest division of matter, at least in the realm of chemistry. Now, if you take particle physics, you'll learn about these things called quarks, which make up what we're going to talk about. But atoms, we call them basically the smallest division of tangible matter. And what they're made up of are these things called protons, neutrons, and also electrons. So how we class these is, and in every atom, it's going to look a little something like this. You're going to have this area in the center, which we call a nucleus. Okay, and orbiting all around, right? This isn't an accurate representation, but it's good enough for where we are. We have these little particles called electrons, which are going to hang out in these things called orbitals. So you can understand that they are orbitals, but because it's orbiting. But we'll learn that it's a little bit different than that in quantum physics and how we describe things then. But it's important for you to understand what atoms are. Atoms have a nucleus, and they have an orbit of electrons around them. Well, I just said that electrons are on the outside. So what makes up this nucleus? And it turns out it's protons and neutrons. So inside the nucleus, we're going to have protons and neutrons, but orbiting around are going to be those electrons. So this is a very important concept to understand. If we split something up a million gazillion ways until we have nothing left that we can divide, we're going to get these things called atoms, which are the smallest units of matter. And they're made up of these three particles. So let's explain the properties of each. And let's kind of get more technical. So if you could, please grab something called the periodic table. You can search it up online or however you wish to get your hands on it. Well, if you look at the first element, you're probably going to see this guy on here. And he's known as a hydrogen atom. And, well, what does this look like, really? Well, in the nucleus, we're going to have a single little dot. And this here is a proton, okay? And orbiting around it, like this, is a single electron, which we can call E minus. Okay? If we then take what's called a helium atom, which is atomic number 2, it will look something like this. So now we have these new kind of particles, right? Instead of an open circle, I have a closed circle. Well, it turns out that the open circles are still protons, but these closed circles are neutrons. And orbiting around, of course, are the electrons. This is how you can understand atoms in the periodic table and where it's coming from. I just wanted to give that as just a basic introduction to how to think about atomic structure. Well, let's think about the properties of protons, neutrons, electrons. I'm going to give you the shorthand notation. P stands for proton, kind of obvious. N stands for neutron, and E stands for electron, specifically E minus. So let's make a little table here, shall we? Let's define the mass. And what we do here is we're going to set the mass equal to 1 for the highest mass thing we have. And it turns out that protons and neutrons both are about the same mass. They're a little different, but for your understanding, they're about 1. And we're going to give this unit called AMUs, or atomic mass units. Maybe a little later in the course we'll explain what that is if it's necessary. But know that the mass of a proton is so indefinitely small. It's like 0.00000, 31 zeros out, maybe like 1/6 something. It's very, very small. I'm not going to even explain how small the mass is. But if you're thinking small, think smaller. That's how we would define it. But we're going to call it an AMU mass of 1 and 1 for protons and neutrons respectively. For electrons, though, they are only a fraction of that. And it turns out, I think, if I remember, it's 0.005. I'll double. So it's 0.0005 AMUs. So what you need to take from this is that when we compare protons and neutrons, they're about the same mass, but if we compare that mass to an electron is only a fraction of the mass of a proton and a neutron. In essence, the electrons are like itty bitty little babies, and protons and neutrons are big fat dudes at a bar or something. But what about charge? Atoms have this property known as charge, and the charge is nothing you can really define. It's like gravity. Well, gravity is just something that happens. Charge is just something that happens. Now, charge means that you can emit an electric field, which you'll learn about if you take physics, or it gives some properties, right, that we'll see later that just pop up. Charge usually means unstableness. That's how you want to think about this. So whenever you hear the word charge, if something is charged, overall charged, it's going to be unstable. So charge typically means unstable, but take that as you will. It doesn't mean much to you now. You'll learn charge if you take a physics course a little more. But it is important in chemistry, so it's important that we talk about it. Protons have a charge of +1. Neutrons, right, if you think about it, neutron, and they have a charge of 0. And that's actually where it gets its name, because the charge is 0. And the way that we probe for charged particles that we'll see later, neutrons are just unreactive, but we know that the mass is there, and therefore we know that the charge is 0. Electrons, on the other hand, they're going to be -1. That's where the E minus comes from. And we'll make a point about this quick. And the last column was going to be, where do you find them? We just talked about this. On the inside of the nucleus, on the outside of the atom for electrons. But let's talk about charge. Remember how I said charge equals instability. Okay, so whenever you see charge, and sorry, I should bring this over a little bit. Whenever you see charge, think instability. Let's go back to our hydrogen atom. Okay, remember I said the hydrogen atom was one proton and a single electron, right? So if we have an electron and we have a proton, well, what we need to know about charge is that if you have an overall neutral charge, sometimes that's just a little bit more stable than if you have a charge. Okay, so when we take hydrogen, just the atom hydrogen by itself, well, we know the proton has a +1 charge, and we know the electron has a -1 charge. So when you combine the two together, you're going to get an overall 0 charge. So when you are asked to find the overall charge of an atom, add up the number of protons versus electrons. If it equals 0, you're probably stable. But let's consider hydrogen with a +1 charge, okay? So we're going to add a charge. Typically, you'll see charges as a superscript. We'll get to that when we get to the notation of atoms. But let's say we have a hydrogen atom with a +1 charge. Well, then you have a proton, but you have no electron orbiting, right? So the proton, in that case, is just +1. All right, this is the idea of atoms. Okay, I want you to get comfortable with charge and the mass of atoms and what atoms look like at the fundamental scale. It turns out that the spacing, right, if we go back and we say we have a proton, we add an electron, therefore there's no charge on this atom overall. So here's an electron. When we consider the spacing between the nucleus and the electrons, this spacing is fundamentally huge. The electrons are not hanging out super close to the nucleus, which is right here, remember. This distance here is incredibly large. Okay, because this spacing is incredibly large, it's going to lead to some things that we've observed to find that, okay? It's just a property of atoms that you need to get comfortable with, and it just gives you a good understanding of what atoms look like. But enough said, let's go through the history and how they found all this, okay? Because it will make a little more sense of like, what is charge and what's all this stuff we're actually talking about. Okay, so the first thing that we've thought about was, well, Dalton. Okay, John Dalton was a scientist in the 1800s, and his publications were in 1807 that really sparked this idea of wanting to understand what an atom is. They really had no idea of what an atom actually looked like at this time. But he came up with some postulates that matter has a fixed smallest unit. Okay, that's the idea of an atom, right? Matter has a fixed smallest unit. That's matter. And then atoms have different properties. Okay, but also, mass has a fixed ratio. Mass of compounds. Remember when we put when we have molecules, one or more elements? That is something that has a fixed ratio. And John Dalton did experiments to find this. So I guess I should say molecules have fixed ratios. So how can we show all this? Like, how did he come up with these postulates? These are his three fundamental postulates. Matter is a fixed has a fixed smallest unit, so atoms, basically, that fundamental smallest unit of matter that we have, atoms have different properties, right? Atoms are, we're going to find, have different numbers of protons, neutrons, electrons. Molecules have fixed ratios. Because they're fundamental units, they have to have fundamental fixed amounts per molecule or per little compound that we have. All right, it has to be a fixed amount. But he didn't know what atoms were at this point. He couldn't fundamentally think about them. He just said, okay, well, I know matter has to have a limit where it's like, okay, there's nothing smaller than this. Atoms have to have different properties, which is something that he found. And then molecules had to have fixed ratios. And I'll show an example of this. So Dalton reasoned in, let's say, for example, a fuel. Okay, when he burns a fuel, isooctane, which is something that's used in your octane rating. So it looks something like this big squiggly line that goes on for a long time. He found that if I had some mass, I could divide the mass among carbon and hydrogen using some sort of method. And I would find 14.8 grams in one trial. So here's one trial, here's the second one, here's the third one. He found that when you burn this gas at some mass amount that you have, for carbon you get 14.8, but at hydrogen you get 2.78. Okay, but when he raises the mass by double, he's going to find a rough doubling of that number. He then went a little bit in between. So he took a fuel amount, he massed out an amount in between here, and he found 19.4 and 3.64. Okay? So what he found, and this is kind of where his idea of atoms was sparked from, is when you divide the amount of carbon to hydrogen that you get. So when you take 14.8 and divide it by 2.78, you're going to get 5.33. So what this says is the amount of carbon to the amount of hydrogen you have, for every 5.33 carbons, you get one hydrogen. And when he burns octane again in the second trial, he's going to also find a mass of, or a ratio of 5.33. And when he went in between, even then he found a mass of 5.33. All right, so what this tells us is that for this fuel source, the amount of carbon and hydrogen remains unchanged no matter how much you mass out. This is his third idea, that mass in compounds and molecules have a fixed ratio. There's a fixed amount of carbon and hydrogen in each. Okay, so this is a fundamental idea of atoms and how he thought about just atoms themselves. But remember, like we said, atoms are made up of protons, neutrons, electrons. Where do these things come from? Well, what we're going to do right now is discuss this idea of how electrons were found and how they were characterized. Well, what happened... Sorry, I got to flip over my notes here. Is one such scientist called J.J. Thomas. What he did was he found that when you have two plates, this is more physicsy, and you apply a voltage across two plates such that you have a cathode and an anode, it's going to emit this little ray across each. Okay, so then he sought to characterize what that ray is. He called this a cathode ray. Okay, so this little ray that's emitted when you apply a voltage across two plates, a cathode and an anode, you get a cathode ray. So what he did to characterize this is he had the cathode sit here and a detector sit here. So this is a detector that's going to detect these cathode rays. And he has a magnetic field right, that has field lines going like this. Now, you don't need to know what field lines are, but a magnetic field that's moving from this plate to this plate. And when he applied the voltage, what happened is a cathode ray got emitted. And the idea is that there's something about these cathode rays, so let's deflect it in a magnetic field. And what happened is, what they predicted was it would go undeflected and stay straight. But what happened was that ray got bent, okay? And that was really confusing to people at the time. It's like, well, why is this cathode ray bending? Well, it turns out that according to another experiment, charged particles move in magnetic fields. It's a right-hand rule. I think it says, here, your thumb is the velocity of the particle, your thumb is the magnetic field, and then the force that you feel is going to be this way. So it actually turns out the magnetic field would be pointing this way, and your force, the force on that particle moves like this, right? So it pushes. If the velocity is that way and the magnetic field is that way, well, then the force pushes it like this to the detector. This is how they found electrons. Of course, they may or may not have known that formula at the time, but they used that reasoning to figure out this idea that these cathode rays are really just these things that we call electrons. So when you apply a voltage across a cathode and an anode, you get electrons out. Okay, now the next thing was sought to characterize, they found that the charge of an electron was 1.6 times 10 to the negative 19. Okay, this is the charge in coulombs, which we'll just call -1, which is the standardized chemistry unit, but it really stands for a charge of 1.6 times 10 to the negative 19 coulombs, which again, you don't really need to know, but that's how small the charge is. 10 to the negative 19 is 0.00019 zeros 16. Okay, so it's a very small amount. Okay, now let's talk about, so we talked about J.J. Thomas's experiment. And what he found was charge and existence. Another scientist did this idea. I think it might have also been J.J. Thomas, although I'm not too sure. The charge and existence of electrons were known now, but what wasn't really known is, well, how much is an electron weigh? Remember, compared to a proton and a neutron, electrons are only a fraction, 0.0005 atomic mass units. So how do we characterize the mass? Well, what they did is they dropped an electron into this little box that has a voltage, positive and negative, and we need to understand the forces acting on this electron. So there's gravity acting this way, but if you know anything about physics, a negative charge is attracted to a positive charge, so the electron is pulled upwards. Okay, this is the force of the electric field. And what they did is they applied a voltage across this such that gravity would equal the electric field. So they wanted to make that equal. And when they did, they found the mass of a singular electron, which the mass turns out to be 9.107 times 10 to the negative 31 kilograms. Okay, so a really, 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 really small amount for the mass of an electron. Okay, and this is only a fraction of the mass of a proton. But how did they find the existence of the nucleus? Okay, what they thought is that, well, when we take just normal matter, all right, and this is the plum pudding model. So for atoms, we know that when we hit it with some energy, you output these things called electrons. But the question remains, well, when I put regular matter in and I don't apply a voltage, there's no deflection. Remember, when we had that electron moving through, it got deflected. But there's a difference here. The electron, normal matter, is not deflected in a field. If we just put regular, like, I don't know, iron shavings through that little apparatus with the magnetic field, it's going to go completely undeflected. So then they devised the idea of the model, and the first one was the plum pudding model, which said that you have these electrons in a ball of positive charge. So there's a little circle, which is the finite volume of that atom. You have negative charge all in it, and you have positive charge sitting all around. But there was an experiment done that kind of disproved the plum pudding model, right? Because this is not what we showed here, right? This orbiting version of an atom. No, we're talking about this, which is not true to what we see here. So what experiment broke this model? Let's explain that. Well, it's this guy called Rutherford, and what he did is he took a very, very thin piece of gold foil. And what this looks like at the molecular scale is just a very thin sheet of atoms. Like this, okay? And he has a source of radiation, so a laser. And he's going to send out pulses to this gold foil. And what he finds when he sends these pulses is that some go right through and some get deflected back, but the majority of them will be sent to this detector, right, which I'm going to call D, this detector. And only, like, let's say 1 out of 10 will get deflected. Well, how do we interpret these results? Because this is a very weird result to get. If the plum pudding model is to be true, when a ray hits, it should be deflected back no matter what, right? Because it's a spherical ball of mass. That's not the case. What's really happening is that we have a nucleus, which is the protons and neutrons, and they have this electron cloud around it, right, with these electrons orbiting. But because of how positive and negative charges want to spread out from each other, they give themselves some room. So when a ray comes in, it can just go undeflected right through the atoms. But however, if they hit that very small nucleus, they'll get deflected, right? So they go through, but then they hit the atom, they get deflected. This is the idea of how they discovered the spacing of the atoms that we talked about. And it gave rise, the plum pudding model showed the idea of the nucleus, right? Or not the nucleus, that there was protons and neutrons maybe in existence, although they may have thought it was just the positive charge. But then they showed that the nucleus is really, really small compared to these electrons, okay? And that experiment was done by Rutherford. That's the scientist's name. I was blanking on it. So Rutherford, he found that there's a nucleus. So putting this all together, we know that there's protons, neutrons, and electrons. We know that for charge, protons have a +1 charge, electrons have a -1 charge, and neutrons have no charge. But when we look at the mass, if we're talking about relative units, protons have a 1 mass, 1 AMU mass, neutrons have a 1 AMU mass, and electrons only have a fraction of that at 0.05. All right, so it looks something like this if we filled out the whole table. And that's the idea of an atom. So remember, you have a nucleus and you have orbiting electrons. Now, I'll make one final note just to kind of tease into the later chapters. This model that Rutherford showed was actually wrong. Okay, if this is a helium atom, it would look something more like this. And this is the idea of an orbital. We'll go in a lot more detail later. But you still have your nucleus, right? Rutherford got that right. But what he didn't get right was how the electrons are orbiting. They're not orbiting in a fixed path. they actually, dependent on this thing called a wave function, they exist in this orbital, which if we look, what an orbital says is 95% of the time, I find an electron in this bubble, okay? So inside this bubble, I'll find an electron, find one here, give more time, find it here. It's flying all around this bubble, and I'll find electrons, if I pause time, all around in here. So that's the idea. Maybe it's a little more closer to the plum pudding model. Just joking, it's really not. There's the plum pudding model, the Rutherford model. This is the quantum mechanical model. So that's atoms in a nutshell. Just keep those things in mind. And then we are going to now get into a little more on atoms and their notation, getting familiar with the periodic tables. So, alrighty, take care, guys. Bye-bye.